Question 6. Sam's going to keep her eye on time for me and shout at me when I've had about 25 minutes. I'll do 25 minutes about on each question, just give you a little bit of time at the end to check over your answers, make sure you've not done any stupid mistakes. Hopefully I can get this done in less than 20 minutes because I think it will be one of my better questions. Okay, so question A, imagine that a hole is drilled from the South Pole through the centre of the Earth to the North Pole, and we've got that diagram in the exam paper. Incidentally, when they put a diagram on the exam paper, feel free to actually annotate that diagram. Don't waste time drawing out again, particularly if it's a complicated diagram. You can write all over the paper, you're handing the whole thing in. By using Newton's law of gravitation, show that if Earth has internal density ρ, ignore air resistance, that's good to know. An object dropped in the hole will perform simple harmonic motion. Okay, now, there is only one thing you need to know about simple harmonic motion. That is, if the force is proportional to minus the displacement, you have simple harmonic motion. Force proportional to minus. In this case, we'll call the displacement R. You have SHM. And likewise, because F equals ma, that means acceleration proportional to minus displacement implies simple harmonic motion. And we can get our period from that proportionality constant. So acceleration is minus omega squared r, where omega equals 2 pi over the period. I guess that's two things to know about simple harmonic motion. Acceleration proportional to minus displacement, and that proportionality constant tells you the period. And really that's about it. Amplitude doesn't affect period, all that kind of stuff. Okay, so I need to show acceleration or force is proportional to minus displacement. So what I will want to do is say, here's my object, here's my displacement from the centre. I just want to work out an equation for the force on that, and I hope that the force is shown to be proportional to minus displacement. Minus means it's an attractive force, it's coming to the origin. Now that bit seems obvious, gravity is an attractive force. Okay, so show that F is proportional to minus R. Now, incidentally, on the exam paper, you've got a few lines to show this. I think it's worth using scrap paper just to work out your answer, first of all, before throwing it straight on there, particularly for sort of more explained questions, sort of more essay-style questions, just to make sure you're putting all the right concepts in a logical way to read it. Okay, so force due to gravity, we know from Newton's law of gravitation that force on an object equals that constant of g times our two masses over r squared, and it's attractive. Okay, so let's say our object is of small mass m. We know that. We know Newton's gravitational constant. So we're assuming we're a distance r, so we know r. So the question is, what is our big mass m? What is m? Now, the question tells us in that hint that when our object is there, what we can do, if we draw that circle of radius r, all that area outside that doesn't contribute. All that mass outside there doesn't contribute. So only the mass at radius smaller than r contributes. So this mass is, well, it's rho times volume, density times volume. Given the density, we can just call that rho. The volume is volume of a sphere, 4/3 pi r cubed. And it's that r there we're interested in, not the whole radius of the Earth, because we're only interested in that mass in there. So that is m. Can you still see that on the camera?
Yep, that's great.
So F equals G, big M, which is rho times 4/3 pi r cubed, times small m, the mass of the object, over r squared, and r cubed over r squared. This is where our r is going to come from. Let's just bring those constants out. So we've got 4/3 pi, we've got big G, we've got rho, we've got m, r squared r, and it's attractive. So F is proportional to minus R. So the minus showing that it's an attractive force. So we've shown that this is going to undergo simple harmonic motion. That was what the question stated, we just check that. Show an object dropped in a hole will perform simple harmonic motion. So that implies simple harmonic motion. Once you've got there, you've got there. Okay, so that's part A done. You happy, Sam? I've
Looks
done
good.
Part A?
Yep, looks really good.